Hello friends, welcome to this video about binary multiplication of signed numbers. The objective of this video is to explain how to multiply signed binary numbers. In the previous video, the basic binary multiplication of unsigned numbers has been explained. Before going into the methodology of signed multiplication, let's explain some concepts related to signed numbers. The difference between signed and unsigned numbers is that signed numbers can be positive as well as negative. In the signed numbers, the most significant bit is dedicated to indicate if the number is positive or negative. 0 if it is positive and 1 if it is negative. As a consequence of this most significant bit dedication, we lose in the range of positive numbers that can be represented, but we gain in the fact that now the computer can also handle negative numbers. Three concepts are particularly useful when managing negative numbers: the 2's complement form, the range of representation, and the rules for sign extension. Regarding the 2's complement form, it is assumed that you have practiced the content of one of our previous videos dedicated to this subject. In any case, at the end of this video, you will find a single slide to help you keep in mind the 2's complement arithmetic properties. Regarding the other two concepts, range of representation and rules for sign extension, I will explain right now these two concepts before going into the methodology of sign multiplication. So, let's go first to the range of representation. The range of representation is the set of values that can be represented using a specific number of bits. For unsigned numbers, the range is from 0 to 2 to the power n minus 1. And for signed numbers, the range is from minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So note that the range is not the same if we are using unsigned numbers or signed numbers. Example, for n equal to 4, that means using 4 bits. For unsigned numbers, the range of binary numbers that can be represented is from 0000 to 1111, that means from 0 to 15, because the smallest number, which is 0000, is 0 in decimal, and the highest number, which is 1111, is 15 in decimal. So the range is 0 to 15 inclusive. Let's see now what happens for signed numbers. We have to distinguish two parts, positive range and negative range. The positive range is from 0000 to 0111. That means from plus 0 to plus 7. And the negative range is from 1000 to 1111. That means from minus 8 to minus 1, because 1000 converted into decimal is minus 8, and 1111 into decimal is minus 1. So altogether the range is from the lowest minus 8 to the highest plus 7. So, in this case, the magnitude of the highest possible number is about half of the unsigned number. Because with unsigned numbers we can reach 15, but with signed numbers the highest we can reach is plus 7. As a consequence, using signed numbers with the sign bit, we lose in the range of positive numbers that can be represented, but we gain in the fact that now the computer can also handle negative numbers. Let's see now the rule for sign extension. As we explained in the previous video, in a system of n bits, the number of bits you may require to represent the result of a multiplication is 2 times n. Example: if you are using 5 bits, the product result of two numbers of 5 bits will need 10 bits. So, when we are multiplying signed binary numbers, we may need to perform what is called the sign extension. Or, in other words, we need to extend the sign bit of the partial products after each multiplication in order that the number of bits match. Sign extension means repeating the sign bit of the number several times in front of the sign number. The rule for the sign extension is: if the number is positive, you fill the front of the number with as many zeros you want. And if the number is negative, you fill the front of the number with as many ones as you want. Any sign number can be sign extended to any number of bits. And with the sign extension, the value of the number remains the same. Example: here, plus 7, which is 0111, has been sign extended to the 8-bit form. For this, we have added 4 zeros in front. And here, minus 5, which is 1011, has been sign extended to the 8-bit form. For this, we have added 4 ones in front. This is the verification that the value of the numbers remains the same, plus 7 and minus 5. When you do this calculation, remember always that the front one is associated to the negative sign. In this case, the front one is located in column 7, so its value is minus 1 times 2 to the power 7. That means equal to minus 128. Let's go now into the main objective of this lesson, the multiplication of signed binary numbers. The method to multiply signed binary numbers is the same we use with paper and pencil for unsigned numbers, with the exception that we need to apply the sign extension we have just learned into the partial products. Let's see a couple of practical examples to explain the method. Let's take a first example of multiplication of two numbers, one positive and one negative. Minus 6 times plus 5, the result is minus 30. Minus 6 in sign binary is 1010. The one in front signifies that the number is negative. Plus 5 in sign binary is 0, 1, 0, 1. The 0 in front signifies that the number is positive. Again, let's recall that in a system of n bits, the number of bits you may require to represent the product result is 2 times n. Here we use 4 bits, so we need to provide the product result with 8 bits. So we need to extend each partial product up to 8 bits. Let's make the multiplication. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. And we add 4 ones in front to extend the number to 8 bits. 0 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. 0 times 1 is 0. And we add 3 zeros in front to extend the partial product up to 8 bits. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. And we add 2 ones in front to extend the partial product up to 8 bits. 0 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. 0 times 1 is 0. And we add a 0 in front to keep up to the column of 8 bits. Remember, with the sign extension, the value of the number remains the same. Note that the vertical sum of the last column produces a carry which is out of the 8 bits. So, this bit is ignored. This is the normal practice because these bits do not participate. The number remains the same without it. This is the verification of the multiplication result. The result is minus 30, so the result is correct. Let's take a second example of two numbers, both negative numbers. Minus 6 times minus 3, the result is plus 18. Minus 6 in sign binary is 1010. The one in front signifies that the number is negative. Minus 3 in sign binary is 1101. The one in front signifies that the number is also negative. Now we make the multiplication and we extend each partial product up to 8 bits as usual. Partial product, partial product, partial product, and this is the last partial product. But attention, we cannot use it as it is. In this case, when the multiplier is negative, we will find that using the same method as in the previous example, we don't get the correct result. Why? Because in this last partial product, we need to do a change. This change is to take into account that the multiplier is also negative. The reason is that to get this last partial product, we have used the sign bit of the multiplier. and in this case the sign bit represents the negative sign, and so the partial product we obtain carries the negative sign. As a consequence, instead of adding the last partial product, we need to subtract it. This is the change that we have to make. As you know, the subtraction is equivalent to adding the 2's complement, which is what we are doing here. This is the 2's complement of this. In summary, the trick of the method is that when the sign bit of the multiplier is 1, then we have to take the 2's complement of the last partial product. So, in this case, once we have sign extended all the partial products, we replace the last one by its 2's complement, and then we make the sum as usual. If in the result there are bits out of the line, we ignore them because do not participate. This is the verification of the result, and we find that with these modifications the result is correct. Plus 18, it's okay. So, in summary, these are the main important points of attention when multiplying signed binary numbers. In a system of n bits, the number of bits you may require to represent the product result is 2 times n. The methodology for multiplying signed binary numbers is similar to the paper and pencil for unsigned numbers, with 2 exceptions. First, we need to apply sign extension into the partial products. And second, when the sign bit of the multiplier is 1, instead of adding the last partial product, we need to subtract it, so we have to replace it by its 2's complement. And remember, with the sign extension, the value of the number remains the same. That's all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. This is the attachment to remind you about the properties of the 2's complement arithmetics. You can check it by yourself. In the next video, we will explain the meaning of right shift and left shift and the difference between logic binary shift and arithmetic binary shift. Thank you.